welcome back. We're finishing up our final example of the second section of Chapter 12 on gravity. So we have an object called a neutron star, and this is kind of a special kind of star. It's just very dense and rotating very quickly. And we have a rotational frequency here of this neutron star of 1 revolution per second. That's this right here. So this star is spinning once every second. So that's tremendously fast. Let's write that down. Our frequency is 1 revolution per second. Okay. And the radius of the star is 20 kilometers. Okay, well, we need that to be in meters, and so we know there's 1,000 meters in a kilometer, and that means the radius is 20,000 meters. Okay, and so it says if it has such and such a radius, and we'll just draw it over here. 20 kilometers, okay, and it's spinning around. That is a frequency equals 1 revolution per second. Very quickly. What is the minimum mass so that the material on its surface remains in place during the rapid rotation? Now, what that means is, well, you'll need to think back to the last chapter where we had rotation and uniform circular motion. We said that if you stand on the equator, you actually weigh slightly less because of your centripetal acceleration. You're partly being flung into space, and you weigh a little bit less than you would at the poles. And then we figured out how fast the Earth would have to be rotating in order for you to actually fly off out into space. Well, that's what we're saying right here. The centripetal acceleration of the planet would have to be such that it would keep objects on the surface. Basically, what we're saying is that there can't be any more centripetal acceleration than gravity. So the centripetal acceleration of the neutron star is going to be, or has to be, equal to the gravity, the gravitational acceleration of the neutron star. That's what we're saying right here. So the centripetal acceleration, and I'll just stay with black here. Okay, the centripetal acceleration of the neutron star is, well, you might need to flip back into your notes into the previous section, but if you recall, we have frequency here and we have radius. Do we have an equation where we can solve for the centripetal acceleration? We absolutely do. And that would be 4 pi squared times r times the frequency squared. Well, we know the radius and we know the frequency. Let's simply solve for our centripetal acceleration. The bad equals sign there. Equals 4 pi squared times 20,000 meters, or you could put 2 times 10 to the 4th meters, times our frequency, 1 revolution per second squared. And you know what, in my calculation I forgot the square, but it didn't matter because it was 1 anyway. So if you square 1, it's simply 1. Got the right answer anyway. Centripetal acceleration of the neutron star is going to be what? It's going to be 789,000. This is a ridiculous number. 789,568 meters per second squared. That's saying that if it's spinning that fast, that's the centripetal acceleration that it has. So, in order for objects not to fly off at the equator of the star, we're saying that that has to equal the gravitational pull of the star at the surface right there. That's what this whole statement is saying. This crazy acceleration of gravity, and these are super dense objects and have super gravity. This crazy centripetal force has to be equal to the gravity of the star if objects aren't going to be flung off out into space. So we're saying that this now is going to be, I'm going to back this up here, this is going to have to be equal now to the gravity of the neutron star if things are not to fly off. They're to remain on the surface. Okay, so the question is, what's the minimum mass of the star? What is the mass of this object? Well, our equation, the gravity of the neutron star is equal to capital G times the mass of the neutron star divided by the radius of the neutron star squared. That should enable us to solve for the mass of the star because we know everything else now. We know the gravity, we know G, and we know the radius. So let's simply rearrange this. Mass of the neutron star is going to have to be equal to the gravity of the neutron star from right up above here times the radius of the neutron star squared divided by our gravitational constant G. So that would be what, 789,568 meters per second squared. That is just ridiculous. Times the radius of the star, 20,000 meters. That value squared, right? All divided by our G, which I'll just write as G because you can just plug that in as G. Now look at this. We've got 789,000 times 20,000 squared divided by G, which you know to be a very small number. That is negative times something times 10 to the negative 11th. We're going to have an enormous number here. This star has to be tremendously massive. If we multiply all that out, and did I even do this right? You know what? Let me do this real quick again. I think I may have missed. Well, I got 2.37 times 10 to the 20th kilograms. 10 to the 20th. I don't even know what that is. Something alien. 568. I'm multiplying this again because I think I may not have squared by 20,000. Divide that by G, right? Oh my gosh, it's even crazier. No, I was absolutely wrong. When I did my calculation, I didn't square the 20,000. It's even bigger. It's even bigger. I just realized that. I'm looking at my my sheet here. Try this. 4.74 times 10 to the 24th kilograms. That is the mass of this neutron star. I know 10 to the 20 to the 6th is million and the 9th is billion. Oh, sorry, the 9th is billion and 12th is trillion. I don't know what 10 to the 24th power is, but it's a huge number. These stars are very small, very dense, and they have a lot of gravity. So that's our answer. 4.74 times 10 to the 24th kilograms. There you go. Hopefully this will prepare you to do some of the practice, some of the homework problems we have. And if you have any questions, come see me. I'll see you then.